Okay, so here's the screencast for the Chapter 1 PowerPoint. There's going to be a little bit of overlap with stuff that I went through in the history of astronomy, but that's okay. There's more of the general concepts in this one. So Earth is very average. We don't necessarily occupy any special place in the universe. A universe is the totality of all space, time, matter, and energy. One of the interesting things about this definition is that it pretty much rules out the possibility for multiverses. Um, so just a thought. Just to give you an idea of the scale of the universe and where we fit into this, this image here, if you want to pause this, kind of gives you an idea of things from like our scale out to the universe scale. Our galaxy, actually, I shouldn't say our galaxy, this galaxy, which is not our galaxy, and we know that because you can't take a picture of a galaxy that you are inside of, and we have never been out of our galaxy. So this galaxy is about 100,000 light years across. So it's absolutely huge, and the Milky Way is about the same. So just to give you an idea of like the scope and the scale of things that we're dealing with here. I'm going to skip over the scientific method because you guys get it in other science classes. Simplest observation of the night sky is that there are about 3,000 stars that are visible at any one time, distributed randomly, but we like to find patterns in things. So here is Orion, and we say that here is Orion's torso, and here's his belts, and here are his legs, and there's his head, and there's like a shield over here. So we like to put patterns to things, but they really are distributed randomly. And the next slide will show you kind of where those things are. Actually, sorry, not this slide. One more slide. So we group stars into constellations. They don't really have tons of meaning. What is useful is that Polaris is almost due north. Not so useful is astrology, which tries to make predictions about star patterns at birth. But if you really look at it, here is where those stars in Orion are. They're all over the place. They're like 1,000 light years apart. So they're not actually as close together as they look from our vantage point. We tend to put things like on a celestial sphere when we start talking about where things are in space. We basically take something that's very three-dimensional and try to turn it into something that's much smaller so we can manage it. So this is kind of where some of those things are. Notice Orion's kind of like in the middle. That's one of the reasons why it's so visible by everyone. When we measure things, we in astronomy, and when we look to find things, we start off with degrees, and so we have 1 arc degree, and then we need to get more specific than that. So if you break 1 degree into 60 equal pieces, then you get what's called an arc minute. But sometimes we need to get even more particular than that, especially with some of our best telescopes that we're using. So if you break 1 arc minute down, you get 60 equal arc seconds. One way to measure these things is called right ascension and declination, which basically takes the equator of the Earth and like protrudes it out into space, and then we base everything from there. That's one good way of doing it, because all these things will be fixed and they'll always be in the same place, relatively speaking. If you look at the Earth's orbital motion, there are 2 different ways to measure a day. You can either have a sidereal day or a solar day, and that's because if you really look at it, if you think of what a day is, most people would say, oh, well, it's 1 full rotation of the Earth. But if you think of 1 full rotation of the Earth, then the sun actually is not at the same point in the sky. Okay, so what 1 360-degree rotation is actually what we call a sidereal day. But if you want to get the sun back to the same point in the sky, you actually have to go about 1 degree more, because we have gone 1 365th of our journey around the sun. So after 1 solar day, you have to spin a little bit further back. So it's like 361 degrees based on this angle. Seasonal changes to the night sky are due to the Earth's motion around the sun. This kind of shows that. So And we're always seeing things that are pointed away from the sun. And this kind of shows that because we see things in space at night. So like right now we're over here in April. So we would be looking out this way. So the ecliptic is a plane of the Earth's path around the sun. We talked about that in the other video. The northernmost point above the celestial equator is the summer solstice. Southernmost is the winter solstice. And that has to do with the angle of the sun. So the angle of the Earth opposed to the sun. So that's 23.5 degrees that we are angled. That gives us our seasons. And this is what happens to the light. If you look at this little gray box right here versus here. So this is if you take the same amount of sunlight coming in, it will basically fill this box at the summer solstice here in the northern hemisphere. But on the winter solstice, that same amount of sun is a much greater gray box over here. And what that does is it spreads the same amount of energy over a larger area. So you get less watts per square meter, therefore you get less heating. So that accounts for the reason why we are colder in the winter and warmer during the summer, because we have less watts per square meter hitting us. So interesting though, since we are mostly water, notice like when we get the least energy is over here, but that's not actually our coldest day. Our coldest day is like over here in January. But that's just because the ocean stores up so much heat and takes a while to release it. Precession is the idea that the Earth's axis actually wobbles over time, and that's what gives us those different pole stars, like I mentioned in the last video. So Thuban used to be the pole star, used to be the North Star. Now it's Polaris. At some point, it will be Vega, 14,000 AD. So it basically wobbles like a top, if you will. Let's see, we're going to skip over a couple things. We have 24 time zones where we don't need to really get into time zones. You guys did moon stuff in middle school, I believe. You did your moon journal and stuff like that. So we have full, crescent, gibbous. Waxing means getting bigger. Waning means getting smaller. So I'm not going to spend too much time there. The moon does give us eclipses every once in a while. This basically shows you. So lunar eclipses happen when the Earth causes a shadow that the moon is in. Solar eclipses happen when we are in the shadow of the moon. Notice it's much harder to get a solar eclipse because the moon is much smaller than the Earth is, relatively speaking. So everything has to be just lined up just right. And this is when you get a lunar eclipse, sometimes called a blood moon because it looks red like that. But the solar eclipse will only happen when the plane of us going around the sun and the plane of the moon going around us match up just right. So that's what this is showing. Everything has to be just right, and you have to have a new moon at the same time. So that's why you only have full solar eclipses once every great while, because everything has to line up just right. New moon, plane of the sun, plane of our orbit around the sun, and the plane of the moon's orbit around us. We already talked about parallax, so we won't spend time there. This is talking about Eratosthenes' experiment that he did to figure out the circumference of the Earth. And I think that's it.